in, in front of entire Cephalo is that about 1.5 year ago, a little more than 1.5 year ago, we were given a instruction from our client, KPMG, that they want to convert their solution into a graph-based solution. We were using NoSQL database at that time, but they decided that they will, for their solution to expand, and since it is expanding and becoming more complex, they will choose a proper database, and they decided to choose the graph database, the Azure Cosmos DB's Gremlin API. Now, that was quite a bit of, I won't say shock, but it was surprising to us. Because in our original proposal, we actually didn't propose a graph database for this solution. We proposed SQL Server. The reason is that the most developers in Cephalo, I believe, are familiar with relational database. And many of you are, of course, working with NoSQL database, like document databases. Now, when you build a solution from ground up, that means the first thing you do is what? You design your domain. Now, most of us have been taught to design a domain according to principles of RDBMS, the relational database. And many of us also know how we can design a domain based on the principle of document-based database. But I believe not many teams in Cephalo are working with graphs. Some teams are, but not many. The design principle that you have to use for designing a domain with graph database is a little different from designing RDBMS or designing document-based database, especially when it comes to normalization or creating relationships. So that is why we thought that the knowledge that we have gained from our work in the past 1.5 years, we will share it with the company. So Shumon Bhai here is our senior developer, and he has profound knowledge on graph database and even with the implementation, because he actually has done it hands-on. So I'll let Shumon Bhai present and help him out with things that needs more explanation, or when the things gets more interesting, of course. Hope you enjoy the presentation. Shumon.
Okay, thank you, Mahfouz bhai. Welcome everybody. I think every one of you can hear my voice. So I'll go straight to the slides. So as Mahfouz bhai said, basically GraphDB is slightly different regarding the RDBMS. So here actually GraphDB more like here is a quote I got. The GraphDB is basically the conspiracy theory, like because everything is connected, interconnected. But relational is more organized. So on the graph design, you need to hop to get the data, and for the relational, we need to perform the join operations. So okay, so our agenda is today basically introduction of graph database, and we'll show some key concepts, and we'll share some things regarding how the domain design with the graph database. Then I'll jump to the Azure Cosmos and the Gremlin API sections, and we will do some comparison regarding the costing and performance. So okay, let's start. So I think as a software engineer, we everyone we have the concept of graph. What is graph? Graph is basically a combination of vertex and the connection, which is called edges. So that is basically the graph concept we know from the book. The graph database design is almost the same. So here there basically are two properties, two main concepts, that is nodes or vertex, and the connection between the nodes are defined with edges. And like RDBMS, the properties can be included in both nodes and edges too. So one thing we have to keep in mind that in graph database, the relationship basically treated as a first class citizens. What first class citizen concept is like in relational database, the connected tables is basically treated as a foreign constraint. So we have to keep a foreign key in another table to make the connection. But here we will get out of this concept. Here basically every nodes have the first class citizen and it will be connected through the edges only. So during hopping we don't need to hop through the foreign key type of things. So the basic example nowadays can be social networks, the recommendation engines, mainly the Reels and TikToks that hops through it. Okay, let me jump through a example picture. Here you see there is there is a lots of nodes and edges. There is some person nodes, that is John, Alice, and Bob, and we can see that how the relationship is maintained between them. So in here, basically, John can be friend with Alice, and Alice also can be friend with John. So and suppose there is a new post by Alice. So this can be liked by Alice also and John also. So if we think it as a relational database perspective, I think everyone getting the idea that we have to have a person table, we have to have a post table, then regarding the connections, we have to have an intermediate table or the foreign key concepts to connect those data. But in here, graph is pretty simple. We just declare the vertex and connect them with edges. And when we want to hop the data, like this post, the graph database is full, who likes that? So we will just take the likes edges and get the count. And another interesting thing that is the dynamicity of the graph. Suppose that we want to introduce a new concept that is follows, like who follows whom. So in graph design, it's actually basically schema-less design we can consider. There is no fixed schema. So if we want to add another relationship, like we here want to add the follow relationship here, we just connect the nodes via the edges with that relationship, like follows. So here, introducing the follows, we can see that now we can easily hop and detect the data. So that's the basic example. So I will represent a case study with the graph and to compare graph with other databases so that the things got more clear. So let's consider we are developing a fraud detection system of a company. So if we want to, the fraud detection system basically are dynamic type of things because the mechanism of fraud and the types, it evolves through time and times. It changes its nature frequently. So here, if we use the graph database here, we can easily traverse the complex relationships like the forwardings can happen through several types of nodes like customers, via customers on the account section or the merchants or any specific locations that will be easily maintained and as I said the dynamic relationship the evolved pattern if the new fork pattern introduced then we can basically easily migrate it add it to this database concept also for the circular relationships like the money laundering schemes like here where the money is transferred between the several nodes on the same system, basically creating a circular loop. So those circular loops pattern can be easily detectable via the graph system easily. And as I said, the schema is very flexible according to different transaction type or behaviors. We can change our schema easily. And now I can compare the things in the relational database. So relational database actually detecting the forwarding system. Actually, we need to traverse very multiple tables with the relationship and joins. And it is notably true that in the relational database system, if we have, uh, I say, after 7 joins, the performance actually degraded. It's obvious thing. So according to the multiple tables, sometimes it will get very complex. Also, the schema is very rigid. If we want to implement another pattern, we have to alter the schema, we have to migrate the data and other stuff. And let's compare with the document database or NoSQL database. Here, actually, it requires the manual relationships and overusing of aggregation or manual processing relationship. Ultimately, it converts it to the mini relational database pattern using so many connections. Also, the common problem of document database is we have to put a lot of redundant data here and there. So, that's basically a simple example. It doesn't mean that okay, graph is the best database nowadays. No, we have to basically understand the use case and where it fits and it sells most. And that doesn't mean that relational database is bad. Okay.
So before we go to the domain design details, it's very important to understand that when you are choosing a database for implementing your solution, which is the best database for you. Graph is from here, you can see clearly that if you create like too many relation, too many joins that has very rigid schema, if you want to change it, suppose you are developing your domain, you don't know your domain yet. It is expanding domain. For example, if the customer give you an SRS and ask you to, okay, give me a software system according to this SRS and I'll pay you. Then what you will do, you'll study the SRS, you'll figure out your entities, you'll detect your domain and you will create relationship, normalize those entities. And for that, the relational database can be perfectly fine. And if later customer asks you that, no, I want to change it, these are the new cases, and then you go to change that, that will become problematic, right? Because anyone who has created a complex relational database, we know that changing the schemas or changing the relation is quite difficult. Now, the document-based databases do not have that problem. You can simply add data, but you have to handle the aggregation and those relationships manually in your code. So graph is offering you, in a way, something in between. But is it the best solution for you? Because designing graph is not always straightforward. You cannot apply your 3NF, 4NF rule and get an anti-domain model out of here. All right.
Okay. Okay. Let's see how we can do the domain design, the graph databases. So as Mahfuzullah is saying, and you first of all you have to understand your use cases. Is this things needed changed over time to time frequently? So do we need any flexible schema? And are the data patterns are basically connected data patterns? Let's think regarding social media networks. So social media is basically interconnected data patterns. Apart from the banking systems data pattern basically fixed and rigid on. We know how to process the data. That the process data of banking transaction is basically fixed. And but in social media section, it's basically interconnected and change the data patterns frequently. Uh, some release there is a property there, and some other next release. You will see that on social media. On some days something is presenting here, and the next day the things got completely changed. So sorry for that. So after that, we have to select our basically which will be the vertex and what is the and which will be the is and what is the properties of that. And the most important thing is that if we are migrating from the relational database, basically it's actually a bit tougher. Yeah, you can compare this with the with functional programming. When the OOP-based programmer shifts to a functional programming section, it's basically gets hard. So first of all, we have to reduce the mentality of thinking database as a table, and there is the foreign key patterns. Then there is a normalization 1NF, 2NF. So graph doesn't work like that. We have to in graph it is recommended that basically one step of normalization is fine. In complex cases, 2NF is good, but no more than that. That's not a specific rule, but that is recommended. Basically recommended that you do a basic normalization. You just separate your vertexes, the basic normalization, and use it with the edges, with the connections. So and when we decide domain with the graph, our first concern will be the data hopping. How we will traverse the graph and how we'll get the data easily. So the first thing will be that we have to minimize the number of hopping, like suppose from user nodes to the post nodes and the lights node. There can be three nodes, but hopping to deep dive hopping can reduce the performance. So we have to design like that okay, there is a user post and user node and there is a post node. So the likes can be edges between them. So the user likes that post. So we have to very concerned about what things we are putting in vertex and what things we are putting in edges. So we don't make it the hop count maximum for that. So that's one thing we have to put. And another thing we need to the hopping can be bidirectional. We have to keep in mind that like user A can be friend with user B, but also user B can be friend with user A. So you see in these things we have a bidirectional attachment with both. So if you think in a relational database, you have to put two entry in the relational database. But in graph, you just pick the edges and just get the both bidirectional output to get your result. Like here, the edges will be friends with, and if friends with, you get the both edges value, vertex value, you will get user A and user B, which is connected through a edge. And also, sometimes, as I said, basically one step of normalization is fine. Other thing, we have to actually denormalize things, or maybe some duplicate data to improve the query performances. Like there is a total sale concept. There is a person, salesperson, and there is sale, and there is total sales. So we can easily hop through the person to sales to get the total sales. But if the dataset is larger, this hopping can be uh, hopping cost many request units. So here we can easily storing those aggregated value on that salesperson node so that we can improve the query performances. Actually, this is one of sample cases. We have to imply those based on our situations, what our application demands. So yeah, and I will just show a short example here. Like here, you see in Graph database, one user ID, one to knows who follows them. So there is a outgoing vertex that's called follows. But if we consider this as a large data set, this will return a vast amount of data. So what can we do? We just here filter it out to make the reduce the dataset smaller so that hopping can be minimalized and partition can be applied. So here we just filter out the first thing of the region so that dataset becomes smaller. And another thing I stored on the bidirectional query. So here user one can follow user B and user B also can follow the user A. So here we don't need to write basically two queries to find out whom follows whose. So we can use the bidirectional support of the graph database to find out the both results. And the last one is the aggregated things that I mentioned in previous slide.
So, gentlemen, I should mention that these queries are written in Gremlin.
Yeah.
So, but there are other graph databases like Neo4j. Their query languages syntax might be a little different from Gremlin.
But the concept will be same.
Concept is pretty much same.
Okay, now as I previously mentioned, let's see some good and bad example. As I said in social media graphic system, the graph database will be a perfect fit. But if you want to build an e-commerce with the category filtering and other stuff, those data basically pattern-based data. So here, using graph will cause overheads. And the second example is the dynamic changing nature of the data. Their graph is good, but regarding the bank transaction, the transaction pattern basically is fixed, and we need to maintain the consistency and other stuff. So their graph is not a good example to use that. Also, regarding the recommendation engine, the recommendation engine basically evolves through each browsing. So after each browsing, the recommendation data pattern changes itself to match the recommendation of a customer. So their graph can be good because graph is very much suitable for experiment. But in inventory management systems, their graph is not a good fit for that.
So what Shuman Bhai is saying that if you have this kind of very defined domain, then it's better that we are not recommending that you go to graph. You can, of course, but at your own risk. But when you have undefined domain or changing, evolving domain, now that is where graph gives you a solid strength. Now it's up to you.
Okay, now basically we'll see all the basic functionality of graph, like indexing and how can we scale up things. So basically in graph database like Azure Cosmos or Neo4j, basically they provide an automatic indexing for vertices and others, which means that the frequently queried things attribute is automatically indexed by the graph itself, which ensures the faster retrieval and supports for filtering for the common attributes. So yes, and now there's the composite index. Composite index basically means that we don't want to depend solely on the automatic purpose. There is some cases that we need special indexing to make our query faster. So there we can actually use multiple properties or combining multiple things to make the composite index and make our query faster regarding that. So you can see the example if the query has the multiple conditions, then actually we need those composite indexes. Okay. And another thing during the indexing of the graph, we basically need to exclude the unused properties because as we saw that graph automatically apply index for each properties based on frequently accessed things. So if we keep the indexing of all properties, it is actually basically will cost us the request unique and also the storage cost will be higher. So we have to take a look at that and we have to figure out the unused properties of graph nodes or edges and exclude them from those so that the storage consumption will be lower and the query performance will speed up. Okay, next slide. Now there is another common concept of database which is partitioning. So graph basically use partitioning that user can define a partition key. Suppose we have a user table. So we have a user table in say in Bangladesh region there is a users. So we can use the partitioning key of like user ID, the unique ones. So what will happen after applying this partitioning? All the user IDs will remain on the same partition, and not only that vertexes, also their associated edges will stay aside those partitions. So if we make the query on those segments, that will give us the better performances. So the basic partitioning strategy is basically we have to choose the high cardinality partition keys. High cardinality means those partition keys that's basically a unique type of keys like user ID. This is a high cardinality, and regarding if we consider the low cardinality, that will be a name. So there will be a same name for many users. So we need to choose the high cardinality personal partition keys to make the partitioning work better. Yes. And another thing, this one is very crucial for graph. When we design the graph things, we have to avoid the super nodes. So what is super nodes? The supernode is that single node which basically connects to a lot of edges. So if this situation happens, it's basically that there is some issues on our design. We have to redesign the graph and make the edges minimal so that there is we have to basically prevent to becoming a supernode. What supernode does when we pick the nodes and edges in one call, so it basically brings a vast chunk of data. That vast chunk of data basically increases the request unit cost. In graph database, basically costing depends on the request units it measures. Like uh, a simple query takes, suppose we are taking one vertex's data, user vertex's data, that's request unit cost will be 3. But if the same data we will query via edges, the how many edges it are connected to the other vertices and other stuffs, which directions, by direction or what, considering those that request cost will go exponentially high. So those things we have to take care of that. And also there is some, as I said, how we can prevent the supernodes. As I said, if there is the many edges, then we need to basically share those edges, like follows. The follows edges can be basically shared on another node. So we have to think out that not creating um, uh, each and every time new edges or things, we have to check out that we can reuse things or not. Also, we can use intermediate node. Intermediate node basically means we can use intermediate partitioning. Actually, the graph query works like that. Suppose we are first making a query, the user that country is Bangladesh. So when we run this portion of query, it will make all the data to one partition. And the interesting fact is that we can continue our query using those segment of data. Basically, it is mentioning as intermediate nodes. So first we filter out the unnecessary things and make the data set precise, and then we can easily continue from that intermediate node to our next query. Like, okay, I first found the user of Bangladesh. Okay, now I want to know which users purchase Bangladeshi shops product. So you see, when we make this node intermediate, our dataset become precise, smaller, and optimized. And this way, basically, we are reducing the multi-hop query. Okay, so now I'll go jump to the Azure Cosmos portion for the graph database used. So Azure Cosmos basically Azure's database service. It actually supports 3 models. One is document, that is no skill. No, sorry, one is document DB, another one is key value pair, and third one is graph. Yeah, it also supports the relational. So the Azure actually, as Microsoft features, the main feature is low latency. In the same reason, it actually works better, and the automatic scaling support. So let's see the Gremlin API. The Gremlin API basically we can consider it as a graph client to retrieve the data from the Azure Cosmos database of graph. Gremlin is basically tightly designed for graph only. So So the key feature of the Azure Cosmos, as we see, that it is the fully managed, it is fully graph database, basically the Azure ecosystems product, and it has the global distribution support. Now, as I previously mentioned regarding the graph database, one important concept is the request unit. The request unit basically defines the cost of each query for read, write, or another operations. So the more complex the query grows and the data size or the connection size or the hopping size, like we have to hop a very deep portion. Regarding on those pattern, the RU consumption goes high. So, so for this, we when we write query in graph, so basically we have to consider about the RU consumption very carefully. The first thing is first of all from the coding side. Coding side, we first of all need to write the efficient queries. Like first we want to use filter to make dataset smaller, or we will hop to the precise dataset that doesn't consist the another extra things to make the request unit heavy. And if the query is much more complex, the not much efficient is possible. So basically, we can predefine the RU based on our workload. So it's actually done by the Azure to review the after reviewing the uh, query performance of previous, we can set the define the RU unit for query.
Now, this is a very interesting concept, the request unit. So when you are using a managed graph database service, you are not only paying for the storage, because storage is actually cheap. The cloud provider will be charging you based on your RU, request unit. Now, that Suman Bhai just shared with you that if you mess up your database design, your queries will have higher RU. That means you are screwed. Now, your manager won't like it, right? You messed up the design, now he's paying for a lot of RUs. Wow. So don't do that. And the second thing is you have to keep continuously optimizing it. The less RU you have, the less your manager pays. So you have to continuously optimizing it, keep optimizing it. Okay.
This is basically a synthetical query just to show you how the query here.
Now this is again written in Gremlin.
Gremlin, yes. So here you see here, I will just explain it very short because it's actually relatable. That is here G means graph. So you see the first one is basically adding a vertex to a graph, the name and specifying the properties. And the second one is basically adding an edge here on this on this vertex. And let's see the graph traversal. How can it traverse? So the graph traversal is simple. We will we can identify the each vertex via its any ID property or any or basic its level. So if we search the vertex with the level, so you see in this when this person runs that person is it's actually make the person available. So the next hopping starts from out. So so it's first actually make the persons available, then it starts hopping to the next person. That okay, find the out edges, which is named nose, and find out the connected vertices. And it's basically a very simple one, and also you see that the hopping can be multi-level. Here you see that we can basically uh, go from one vertex to another and give down how many we want. Here you see the two level of hopping used, that two hours are used to hop from vertex one. Okay, now
Yeah, this is the most interesting part.
now we can talk about the costing of the Azure Cosmos.
So, gentlemen, this is very important because nowadays, when the client asks you to design a software or give them a domain, the first thing they will ask you that, hey, how much do I have to pay for it? Okay, so I mean, this is very important. Now, Suman Bhai has a billionaire client, but they are exceptionally cheap because actually, people who has more money they do not want to spend money. People who have less money they want to spend more. Anyway, that is what Suman Bhai is getting from the client. So this is very important. Pay attention to it, please. Go ahead.
Okay, as Marcus will also said earlier, actually in Graph concept, the storage actually basically cheaper things. Azure provide the storage at a very cheaper rate, but it charges based on RUs. So so you have to be careful. It can be a trap if you are not careful. Suppose you forgot that that node became a super node, or after running a graph uh, period of times, you have to look out the relations and data things that yeah, this node becomes actually super nodes and this has so many connections. So as because it is a schemaless database, so you can easily modify and things. You don't even need to migrate the data. You just change the edges, the connections and pattern easily. Not like the RDMS. And so regarding the in Azure Graph, they actually charges you based on the RU, and the storage they also charge for storage, but comparing the RUs, the storage charge is minimal. And another thing they charge regarding the data transfer over multiple regions.
Sure.
So there you have when you design a app that is globally distributed, that has several regions, and you need to transfer data or write the queries that will affect their. If the queries affects quickly, then it will charge one kind of things. If you accept some latency, then it will charge a little less. So these three things basically are the pricing model for the Azure Cosmos. And for the cost component, so as we said, we can use the provision throughput that we can say, use maximum 200 RU, do not cross that. That is basically a provision throughput, the fixing the RUs. If it overlaps,
Yeah.
so the fixing the RUs, so it will keep you safeguard. Okay, that query will not exist. And also you can use the basic features that is auto scale. Also you can monitor the RU users and take decision according to that. And again, the cost estimation analysis of the relational database, as you already knows, if the data set is highly connected, then GraphDB is definitely cost effective. And that if the query performance is critical, then here also GraphDB is good. And if we need frequent traversal with the complex relationship, here also GraphDB is good. But
only if you can design it well.
yes.
Otherwise, you are screwed.
And the relational DB is definitely effective when the data is organized and structured. There, using Graph will be a hilarious decision from my views. and where the simple lookups and needed rather than deep relationships. And there, I don't see any point of using graphs. The relation DB is very much fine. And the performance analysis, actually, I have mentioned it in previous. Here I just give a short side. That's if the relational heavy queries, so the performance of graph will be better. And according to the Microsoft, Azure actually offers the good latency and high throughput for graph queries regarding to the relational database. And the complex graph queries that which have a deep relationship, their also performance is good for graph. The concurrency management is so basically Graph doesn't support fully concurrent system. Actually, uh, Graph and the original Graph of Neo4j, it supports the transaction-based system of Graph queries, but the Microsoft basically migrating from Neo4j and making the Azure Cosmos. So the transactional support having been shown it in for the Azure Cosmos. So they are actually we have to use the optimistic concurrency, the ETAG based for the conflict resolution. We can set the rules that okay the last write wins. And for the consistency level, either we have to use the strong consistency that if we change the data in one replicas, it will immediately affect on another replicas, or we can go with the eventual consistency that there will be some latency, slow by slow, all replicas will be affected. Those things basically works for what is it, the reels because in the reels of social media, we don't necessarily need that all replicas must be up to date immediately. Their latency can be accepted. So yeah, as I say, so managing ACID basically here as it doesn't support transactions, so we have to ensure that the query will here basically in for Azure Cosmos we follow that query will go one go with the query. That means we write the queries and try to execute the query as a whole. If the query succeeded, then the write operation will happen. And if it is fails, no operation will happen. So we just execute the whole query together. As consistency isolation are same like others. So in our I'm very close to finish. So I will just give a short note about our project skills. So when our client decides to go with the graph, because our domain model basically was dynamic, we have no clear definition of our domain. That's why we use the graph database. Also, one thing that since it is a new, we don't have any ORM, so we have to develop a mini ORM for that using the JSON serialization and other to make the data layer happens. And regarding the concurrency stuff, since it doesn't yet support a transaction, we have to use the distributed cache mechanism system that is basically combining with the distributed cache and graph query execution. We maintain and reduce the concurrency issues. So yeah, sorry, that was the long presentation and most of it technical. Actually, the content is like that. I tried to explain. So now, if you have any questions, please feel free. You can ask on chat also if you have any question.